Right, thanks for the introduction. I'm going to talk about language-integrated privacy-aware distributed queries. So this is joint work with Mirko Köhler, Daniel, who is our student volunteer today, Mira Mezini, all of us from TU Darmstadt, and Philipp from KTH, and Sebastian Erdweg, he's in Mainz currently. Let me remind you the case of Cambridge Analytica. This had quite some exposure in the press. Essentially what happened was that a company was running a survey and users would accept to give their personal data to this company, but because of how the Facebook API is structured, it was possible for this company to access many more data than those related to these users, specifically all the users in their network. This ended up pretty badly. Almost 90 million users were affected. These are Facebook numbers. This is the market capitalization of Facebook during the days of Cambridge Analytica, and you may remember the videos of Mark Zuckerberg showing up in front of the US Congress. And even if you don't use social networks personally, this may still affect you. It turns out that Cambridge Analytica has been involved both in the Brexit and the Trump campaign. So this is just an example of how data privacy is crucial in computing systems and how we really need to precisely control where private data may flow inside a distributed system. And this is especially true when systems are highly heterogeneous and complex, like IoT, like systems that include IoT devices, mobiles, for example, that belong to different users. And this is also true in a cloud environment. So companies are moving towards an hybrid cloud model where they have an in-house cloud where they can compute some of the operations, and some others computations are offloaded to an external cloud from a third-party provider, for example, Amazon. In this setting, privacy is totally important, and it plays a crucial role how you deploy your computations. Let me give you an example. This is taken from the hospital IT information system, which is described in this paper from '99. The paper describes the structure of the information system with the tables and their relations. And this is a query from that information system. The query is based on 3 sources of data. There is a person database. That's a database of personal informations of users. A database with the patients for the hospital. And then there is a knowledge database. This is medical knowledge that correlates essentially symptoms to diseases. And what this query is doing is to retrieve personal data that is relative to the patients of the hospital, and specifically those patients that show the symptoms of an allergy. So as we all know, one can map an SQL query to a relational algebra tree, and this is how the relational algebra tree looks like for this query. We have these 3 sources of data, and we are performing a selection on the diagnosis being allergy for the knowledge database, and then we are performing 2 joins before getting the final result of the query. And if you look at different deployments for these operators in a distributed system, you get a very diversified performance profile. So in the red bar, we are running all the computations only on a single machine. In this second bar, we are distributing the computations among multiple machines in the cloud. And in the last bar, we are still distributing the computations, but we are doing that in a sort of smarter way. So we are pushing a selection close to the source of data, which is a well-known optimization to speed up the system. So placement is crucial in this class of system for the efficiency of the result. And in this talk, I'm going to talk about SQL, so SQL, which is a programming framework that ensures both privacy and efficient placement for distributed computations under the assumption that data sources are distributed and that nodes in the distributed system have different access permissions. So let me go back to the relational algebra tree I showed before, and we can look at how these operators can be deployed in a distributed system. So this is the first possible deployment. In this case, we have the free sources, yellow, orange, and green. So these are the data coming from the patient DB will be labeled by yellow, and similarly the data from person DB and knowledge DB will be labeled by orange and green. And in this case, we are just moving the data to the client, and we are running all the operators, the two joins and the selection on the client. So this specific deployment is pretty bad from a performance point of view. Imagine the client is your mobile device, then you are running all your computation on your mobile device. On the other hand, this deployment is very safe from a privacy point of view, and it's easy to see why. Under the assumption that the patient database machine can access only its own data, so the host permission is yellow, and similarly the person database machine and the knowledge database machine only can access their own data. Then as soon as we join, for example, the patient data and the person data, we need to run the join operator on a machine that has access to both yellow and orange. In this case, the client can read the result of the entire query, so the client can read both yellow, orange, and red. So running all these operators on the client is privacy preserving, and this is a privacy preserving deployment. We can do better from the point of view of efficiency. For example, under the assumption that we have more flexibility and the machine with the patient database can execute any computation, so it has access permissions for both yellow, for yellow, orange, and red. Now we can move the selection and the two joins to this machine. And now on the client, we are just receiving the result. So if the client is your mobile, now you're happy because there is much less computation going on there. This is also, so this is better from a performance point of view, and it's also, again, privacy preserving. We can improve on the performance side with a classical optimization. We can take this selection, and instead of moving all the data from this machine to this machine, we can push down the selection and do a deployment with this configuration. And because this selection is working on the same data that originated from this machine, this is also a privacy preserving deployment. Not all deployments are privacy preserving. This is an example of a non-privacy preserving one. Here we are moving the data from the person database to this other machine, and we perform one join here, and then that's fine. But then we try to perform the second join on this machine. This machine has access permission only for red data, but the join requires access permissions for all the data. So this is a non-privacy preserving deployment. So the point is some deployments are privacy preserving, some others aren't, and some are better from than others from a performance profile, and we want to reason about these two things together. So our system has a two-steps placement mechanism. In the first phase, we call it placement space reduction. What we do is to take the relational algebra tree and conceptually generate all the possible deployments and check which deployments are privacy preserving. What we do in practice is to collect all the constraints that give us the privacy preserving deployments. We don't really generate the deployments because this would lead to a space explosion. And those deployments that are privacy preserving get to the next phase, which is the cost model optimization phase. We feed these deployments to a constraint solver, and which also takes into account a performance model of the system. And from there, we get the single deployment that is both privacy preserving and optimal from a performance point of view. So from a more high level perspective, this mechanism receives as input a specification of what a secure execution is. So it's a calculus for secure SQL. We feed labels for data privacy, the definitions for data privacy, so the level of privacy of data, the permissions that each host has in the system to access those data, a system specification that tells us the speed of the links between hosts and the processing power of the hosts, and a cost model, which is essentially the thing we want to optimize. For example, a combination of runtime and CPU consumption, say, and bandwidth. So we evaluate the approach in the cloud using AWS. Operators are containerized using Docker. And we base the evaluation on an adaptation of the TCP/H benchmarks. TCP/H is a kind of standard benchmarks for database queries. What it gives you a database schema and a list of queries on this standard database schema. For example, reporting the amount of business that was built, shipped, and returned by a company in a certain amount of time. So TCP/H doesn't have privacy labels, so we added the privacy label ourselves. And this is an extract from the performance results. Here, the black line is a reference based on a single client deployment, and these four things are different cost models. So we are optimizing for different things. Yellow is a non-privacy preserving placement, and red is a privacy preserving placement. And if you compare the non-privacy preserving placement and the privacy preserving placement, the runtime is pretty similar. So basically, we show that with our framework, you can get a privacy preserving placement at a not so much higher cost than a non-privacy preserving one. And this comes without trading performance for memory. So the memory consumption is pretty much the same. There is more you can find about this in the paper. So we have a full formalization of secure SQL. We formalize the placement algorithm, and we prove that the placement is privacy preserving. And the point of this formalization is that the placement is formalized as a program transformation. So we can use PL techniques to carry out the proofs, and specifically that the placement is privacy preserving. We have also much more evaluation, and specifically we show how the system performs with different cost models, and that's all in the paper. So in summary, I present a model for language integrated privacy aware distributed queries. This is needed in edge and hybrid cloud environments where you can have multiple deployments, and some of them are privacy preserving and some aren't, and some have better performance profile than others. we have a two-step process where we generate all the privacy-preserving deployments, and then we pick up the one that behaves better from a performance profile, and we show that using a privacy-preserving deployment doesn't have worse performance than a non-privacy-preserving one. So SecQL combines privacy with efficient placement in distributed computations. You can check out our implementation, and that's all I have. And if you have any question, I'm happy to answer.
We have time for a couple of questions. So let me start us off. So I'm curious to hear your thoughts on how this might interact with replication, for example, where the same database may be closer or further in different regions and when the client is.
So we didn't look into replications yet. So we assume that the data sources are the same. A very interesting case would be replications of data that are not necessarily available. So if you consider the previous talk, combining the two systems would be a very, very interesting research challenge. Right?
Okay, so in the database world, there is like a huge body of work that's been done on distributed databases, and where they prove like properties like parallel correctness to reduce the number of communication that you have between your distributed databases. So, and now in the programming language community, of course, with the advent of big data and all of these, the data that we have in these companies, this becomes an issue that we can not really ignore anymore. So how do you see this collaboration between us and the database people?
Well, so privacy preserving, the distributed privacy preserving queries is an active research field also in the database community. So there are papers on this topic that have been published in the last months, for example, with an approach that is pretty similar. What is a bit unique about this work is that we use PL techniques to carry out these proofs, so that the proofs that in the database community are often ad hoc on tree transformations over trees, we can do that using type system techniques, like essentially induction on derivation trees. And that's the crucial thing.
Okay. Thanks.
Well, thank you for your talk. I just have one question. It's when you talk about benchmarking, you have figures where your computation with privacy constraints can beat the computation without privacy constraints. How do you explain that?
Because the model is not perfectly accurate. So we have a model of the system based on monitoring, and that cannot perfectly predict the performance of the system. So something a very interesting area of future work would be better modeling of the system using, for example, queuing theory and so on. Yeah, that's a very good point. Thanks.
Okay, thanks.
Okay, let's have one last quick question here, and then rush to lunch.
So this is great work. I was wondering, I mean, we can think of optimization coming much earlier in the process when you can actually, the equivalent of refactoring the database, you can have a migration, an entire migration to make sure you optimize on specific classes of queries, right? Mm-hmm. And there, have you thought at all about how migration with specific privacy concerns would work? Like you could use some of the transformation techniques, I'm assuming, and that's the question. Could you use them to transform the database, optimize the database in a specific structure while preserving the guarantees that you need?
So yeah, so the focus is on the work is really on formalizing this approach using PL techniques. So we used textbook optimizations, like pushing down selections, and we do that early on as soon as we have the model of the query, so the relational algebra tree. We didn't do much in the direction of advanced optimizations or distributing data among databases to optimize the query, for example. That's definitely a very nice future work. Yeah.
Right. Thanks, Guido.
Thanks.